Welcome to the presentation on phase transfer catalyst. 1-chlorooctane does not undergo nucleophilic substitution with sodium cyanide even on heating with the stirring for several days. Actually, we expect 1-chlorooctane to undergo nucleophilic substitution with cyanide to give 1-cyanooctane, but that does not take place. However, when a little amount of an appropriate quaternary ammonium salt is added to this reaction mixture, the reaction takes place immediately and gives the maximum yield of 1-cyanooctane. The quaternary ammonium salt used here is acting as a phase transfer catalyst. Similarly, the quaternary ammonium salt, triethyl benzyl ammonium chloride, which is referred to as TEBA, is used to accelerate the two-phase reactions of cyclohexanol with benzyl chloride and phenylacetonitrile with ethyl chloride to obtain cyclohexyl benzyl ether and ethyl phenyl acetonitrile respectively. The reactions are given here. Cyclohexanol reacts with benzyl chloride in the presence of sodium hydroxide, the aqueous sodium hydroxide, to give cyclohexyl benzyl ether. This reaction does not take place in the absence of triethyl benzyl ammonium chloride, the phase transfer catalyst. The reactants cyclohexanol and benzyl chloride are present in the organic phase, whereas sodium hydroxide is present in the aqueous phase. This sodium hydroxide has to react with cyclohexanol to generate the alkoxide, which has to react with benzyl chloride. But cyclohexanol and sodium hydroxide are present in two different phases. Therefore, the reaction does not take place. But when we add the phase transfer catalyst, the reaction becomes possible. Similarly, benzyl cyanide reacts with ethyl chloride in the presence of the aqueous sodium hydroxide to give ethyl phenyl acetonitrile. This reaction also does not take place in the absence of the phase transfer catalyst. For this reaction to take place, first of all, sodium hydroxide has to abstract a proton from this methylene. The acidic hydrogen present here has to be removed by the base, but the benzyl cyanide and ethyl chloride are present in a separate phase and sodium hydroxide is present in another phase. Therefore, the reaction between benzyl cyanide and sodium hydroxide is not possible, whereas the reaction becomes possible when we add a small amount of the quaternary ammonium salt, triethyl benzyl ammonium chloride. When the reactants are present in two different phases, namely organic phase and aqueous phase, a reaction between them is not possible because one of the two reactants is in organic phase, the other one is in aqueous phase. They are in two different phases and they are not in contact with each other. Therefore, the reaction is not possible between the two reactants. When we add a small amount of phase transfer catalyst into this reaction mixture, it facilitates the migration of one of the reactants from one phase to another phase where the reaction can take place. When one of the two reactants is soluble in water and the other is soluble in organic solvents, we have to make use of a phase transfer catalyst for the reaction to take place. As we have already seen, the reaction between 1-chlorooctane and sodium cyanide does not take place in the absence of a phase transfer catalyst because this 1-chlorooctane or N-chlorooctane is present in the organic phase and sodium cyanide is present in the aqueous phase. So 1-chlorooctane and sodium cyanide, the two reactants, are present in two different phases. When we add a quaternary ammonium chloride salt, it goes into the aqueous medium and there is an ion exchange takes place. The quaternary ammonium chloride exchanges the chloride ion with the cyanide and becomes quaternary ammonium cyanide, and then it travels to the organic phase. Now the cyanide ion, which was originally present in the aqueous phase, has moved to the organic phase and it is now available to react with 1-chlorooctane. Now the reaction between 1-chlorooctane and cyanide ion takes place to give you 1-cyanooctane. And this reaction, as we have already seen, is not at all possible in the absence of the quaternary ammonium salt. It is the quaternary ammonium salt that is taking the cyanide ion from the aqueous phase to organic phase, and it is transferring one of the reactants from aqueous phase to organic phase where the reaction is taking place. So the quaternary ammonium salt is playing the role of transferring one of the reactants from one phase to another phase for the reaction to take place. A list of quaternary ammonium salts which are used as phase transfer catalysts are given here. In all these quaternary ammonium salts, we find 4 alkyl or alkyl and aryl groups present along with an ionic part. So the alkyl and aryl part of the molecule is non-polar. It is made up of only carbon-carbon and carbon-hydrogen bonds. Since it is non-polar, it is hydrophobic and it is miscible with organic bases, organic solvents. Whereas the other end of the molecule, which is ionic, makes it miscible with the aqueous phase. So in all these quaternary ammonium salts, you can find the alkyl and aryl groups present. Therefore, these quaternary ammonium salts are miscible with organic phase as well as aqueous phase. That is why they are able to move between the organic and aqueous phase, and they carry the reactant from one phase to another phase. The activity of the phase transfer catalyst of the type R4A plus X minus is decided by the chain length of this group R. With the increase in chain length of this group R, the miscibility in organic solvents of the phase transfer catalyst increases. Not only the chain length, there are 4 R groups. The 4 R groups may be the same or different. Therefore, the combination of 4 R groups is another factor that is deciding the catalytic property of the molecule. The A plus, the central atom, in quaternary ammonium ion it is nitrogen, and there are other phase transfer catalysts where the central atom is different, like phosphorus, arsenic, antimony or sulfur. So even the nature of the central atom that is present here is deciding the catalytic property of this molecule. And then the introduction of some functional groups into this group R is another important factor that is deciding the catalytic activity of the phase transfer catalyst. So maybe in the next module we will discuss in the conversion of alkyl halides into alcohols with aqueous sodium hydroxide, we are making use of a phase transfer catalyst called beta 9, which has got a functional group carboxylate ion in the group R. Therefore, introduction of a functional group into this group R is altering the catalytic property of the molecule. And then the nature of X minus that is present here is another important factor that is deciding the catalytic property of the molecule. Introduction of chiral centers into this group R or making the central ion itself a chiral one is also another factor that is altering the catalytic property of this molecule. Some of the advantages of using phase transfer catalysts in a reaction involving more than one phase. Under the influence of phase transfer catalyst, the reactions are taking place at a faster rate, and there is no need of using any vigorous conditions like higher temperatures, and there is no need of any anhydrous conditions since water is used as one of the phases. With the help of phase transfer catalyst, the anion which is introduced in the aqueous medium is available in the organic phase where its nucleophilicity is more. When the anion is present in aqueous medium, it is existing in a hydrated state. So it is highly solvated in the aqueous phase. When it moves along with the phase transfer catalyst to the organic phase, it is not remaining solvated and it is free to react as a nucleophile. Therefore, in the organic phase, its nucleophilicity becomes more. And when we use the phase transfer catalyst in a reaction involving more than one phase, we need not use expensive aprotic solvents. And these are some advantages, and some of the other applications of phase transfer catalyst we will discuss in the next module. Thank you.